Yeah, so it's a pleasure to be here. Maybe some of you guys saw something probably somewhat similar, but fortunately, these discussions have always been very interactive. And so, as much as you have questions or want to use this as a forum to learn something or say something, I'm happy to facilitate that, and I'll be kind of the moderator, I suppose, in some ways. So I'm a professor at the University of Texas at Dallas. I've been there since 2016. When I started there, I was a professor before overseas, and so when I came back, I was really getting into this idea of security, and from a kind of a physics-based perspective. So I'll give you a little bit of a flavor of that without letting you glaze over too much. But a lot of what I want to talk to you about today is some of the more recent stuff that we've been doing, where it's really come as a derivative of our work on security. And when I say security, it really means safety and security together. And the specific application for autonomous driving. And so tell you a little bit about some of the stuff that we've been doing and my understanding of what is a very changing environment in the commercial space. I was really glad to hear already a number of people are plugged into the capstone projects at UTD, and so I was really pleased to see that. I'll share with you a couple of the things that I know that are happening around UTD, and I'm glad to learn even more of the stuff that I'm certainly not aware of everything that's happening around campus. As a researcher at an academic institution, it's a little awkward to be working in an area like autonomous driving, which is one that's very dominantly industry driven at this point, pun intended. But it's there's clearly a capability difference between anything anybody's doing in academia and what you see out there on the roads right now, depending on which city you're visiting. So, I mean, here's a smattering of a couple of different vehicles that we've got Waymo, Google's, we've got Zoox, which is Amazon's. We've got a couple that are no longer in existence because this is a high enough dynamic environment where essentially people have invested untold amounts of money and then essentially decided that wasn't going to work. So then that got bought or sold or moved on to somebody else. So, but what is for me, what is the value proposition of working in this area if I'm never even going to possibly be able to compete with all of this? So it all comes back to number one, I am at an engineering education, place of education. So number one, I have to build a workforce that's ready to work on these problems. And very few programs have very dedicated courseware related to this. So this really comes outside the conventional courses. And so it gives them hands-on access to working with these problems, even if it's at a lower level than what's happening there, they still get some exposure. But at the same time, I think that there is a compelling case for doing something even in research. And so what we are trying to build, the group that I've been working with is we're trying to build what I call a research-ready self-driving software stack. And so the term software stack doesn't always make sense to a lot of people. It essentially just means that there's a lot of different algorithms that are working and passing things along the way. So it's kind of layered, and so that's why we usually call it like a stack. We want to build something that's open source, that's modular, so some nice properties that oftentimes people want to use with building software, but by and large, research ready. And so what is research ready? Research ready really kind of means that I could actually maintain this code base and I could actually run it with some students that have to figure this out year by year. There are a few open source tools for autonomous driving at this point. There weren't a couple of years ago when I kind of started this. So AutoWare is one of them. So that's an open source project. But what they're really trying to do is trying to build like a full level 5 eventually autonomous driving platform. And that's kind of beyond the scope of anything that I could possibly hope to maintain in my lab, even though that's already pre-built. Running that, installing that, operating that takes a team that's very large, and it takes a lot more expertise than what I can drill into some students, or even that I have. So again, research ready is emphasizing that this is geared towards research. It's geared towards people that if I want to collaborate with someone in the hardware group at UTD, they have a new radar sensor that can do some new things and want to test it out, how that changes an application of autonomous driving. I can be there to provide literally the vehicle for that. If somebody has a new machine learning method, they want to show how it generalizes to unknown classes. They want to apply that. come to me, and then I can actually put that into our stack, and I can put it into a simple enough arrangement that they could kind of see how it gets changed. And I'd like to make this swappable so that I can say, okay, I'll bring in some very, back in physics, you say, okay, we're going to talk about the Earth, we're going to model the Earth. It's a point mass. And then you go on from there, right? So we can have the point mass version of this model, but then we can also have the much more complicated version. So I think there's a value proposition for having all of these different, more complicated versions of this. So I said it was about education as well. So these are 3 different pictures, or I guess 2 different group pictures. So it's been going on for about 5-ish years. The last couple of years, I've been really happy to see about 20 or more students involved across the engineering school. So this is including electrical engineers, computer engineers, computer science majors, mechanical engineers, and so on. And so really bring together a lot of people. And I think the cool thing about autonomous driving is the one that genuinely needs all of these people to be present. But to date, this has been almost entirely an undergraduate effort, and that's really been purposeful. There's a lot of research to be done on the graduate level, and that's happening more and more. But this project has really been to be a place for undergraduates to experiment and learn. Okay, so that's kind of what we're going with. If we do just kind of step back and figure out what is an autonomous driving platform, what does that look like? Pretty much all systems kind of boil down to essentially these 5 layers. I'll call them 5 layers. This first one is about sensing, so it's pulling in information from the environment. So this could be a whole host of different sensors that vehicles can use. Things from GPS, which is just kind of like exactly what you're getting off your phone. It could be something more like a camera system. Maybe it's a 360-degree camera system. Maybe it's a thermal camera system. Maybe it's a LiDAR, which is essentially sending out laser beams and getting back a point cloud. Could be radar, which there are a bunch of different technologies for all of those. So there's a lot of different ways for essentially this brain to get information. Then it has to kind of process that into something meaningful. And so that's what perception is all about, taking raw sensing into something that's kind of more meaningful. And so that could be classifying objects in a camera image. Could be using LiDAR 3D point clouds in order to classify an object. It could be doing things like essentially looking at an image and breaking it up into, here's a place where I can drive, here's a place where I shouldn't drive. So it's kind of like semantic segmenting an image and things like that. So there's a lot of first level processing that can be done. And then there's even like subsequent processing where you might want to leverage the fact that you know what an object is in order to know what it should do. And that kind of leads us into prediction. And so prediction and planning is really this idea of, I actually need to know what things around me are going to do. I can't just have a static snapshot of what's going on. And then I'm going to build in my understanding of what these things are, this kind of semantic understanding of context, and then figure out what I expect it to do. And that allows me to start planning what I ought to do in the future in order to stay safe and still achieve my goal. And then that propagates from that planning, then that propagates into things like actually actuating, making control, making the vehicle do things. And so there's this handoff from these different layers. And that's kind of what most of these autonomy stacks will look like. Some of them might try to jump over some things. Like, for example, right now, our stack doesn't do a whole lot with prediction. We kind of use a static version of what's around us in order to plan, and then we just expect that we iterate on that fast enough and we drive slow enough that we don't have to worry so much about like predicting where things will be. And so in the scope of what we're interested in doing, we're kind of interested in leveraging our understanding and the simple versions of what we're putting together in order to provide transparency. So one of the things I think about is how I can contribute locally to this particular problem is, we're still in Richardson, or are we in Plano at this point?
Richardson.
Okay, we're in Richardson. So I live in Richardson, UTD is in Richardson. I'm interested in working with the city of Richardson if Waymo actually you read every couple of months, somebody's going to deploy in the next 2 years an autonomous driving solution. This has happened for the last 5 years, someone's been saying this. So it hasn't happened yet, but someday it's going to happen. Someone's going to want a taxi service. Uber's finally going to deploy a self-driving taxi service in Richardson. what is Richardson, the leadership there, how do they negotiate the challenges that are associated with the risks that are associated with that? I think that maybe the proficiency that we're developing in this group could be a local skill set that we could use in order to like help guide Richardson along.
Yeah, it's interesting. My daughter was just in Austin, and Waymo's down there, and they're fully deployed down there. I was recently in California on a trip, and Waymo was way all over the place. In fact, we saw in their history of computers, they actually had a Waymo mobile that it just, you walked in, it was like a little mini living room. They had no steering wheel or anything, and it was a car that would just drive you around. That was their prototype, you know. But it was really interesting seeing so many of those cars out and about. You know, my daughter paid for her taxi ride from her hotel to wherever she was going in this Waymo mobile. Yeah. Instead of the video, the steering wheel's turning by itself and everything.
I mean, it's very real.
It's very real.
It could come. So that's and Arlington is doing some pilots with certain scopes and things like that. So very much could come here. And so then, yeah, the question is, how do we advise them on, you know, even something as simple as, you know, if you're going to do construction now, what kind of signage do you put up in order to, you know, protect the workers the best, protect pedestrians the best, and so on. So those are the kind of opportunities where I think locally there's an opportunity to be someone that can advise on that. So that's a direction where I hope that this expertise builds us. In terms of what we're building, and I'm glad to have comments and questions. So if anybody has anything, I'm happy to chat through it or hear what you want to share. This is really small at this point, but this is really just a schematic of some of the things that we've built out. So again, our stack is relatively rudimentary at this point. Each year we're kind of building and adding to it, but it's already fairly complicated. Every single blue node represents essentially a piece of our modular stack that's doing a different job. And that's really how this works. So I'll kind of show you a couple examples of some student work, but here we use what's called ROS, Robot Operating System. It's technically not an operating system, it's a misnomer, but it is, it's a way of building kind of modular pieces that then communicate with each other. So there's lots of messaging going on, and I'll kind of talk a little bit about that. But the whole idea is to make it modular, make it able to write one node and have it live in this ecosystem, have multiple different versions of this, so we can kind of swap these in and out if you want a more complicated version or a less complicated version.
Do you use the standard Canvas on this, or do you have your own proprietary network?
Yeah, it's a great question. So I kind of listed CAN here. I'm not going to assume that you can read anything on the slides, but CAN is listed there as a way of getting sensing. So one of the ways that we could use CAN is to just use the built-in vehicle's estimation of speed, for example. So we do harvest some information off the CAN bus in order to send this kind of messaging around. A lot of these nodes reside on the same computer. So they are modular pieces that are running typically on separate threads or something, processes that are now communicating between each other. Recently, we have introduced a second computer that handles a lot of our sensor processing, since that's a dedicated task. And so now there's also message passing between the computers that's done over Ethernet. A lot of this communication, like sending all of the LiDAR measurements, that would kind of be very busy over the CAN bus. So we would I think we would hit a limit at some point. And so most of this message passing is all done either intra-computer or between. Yeah.
So there's the Comma AI project. Are you guys leveraging that?
You say
Comma AI?
Comma AI, yes. This is the
open source.
Karma? Is that
Comma, C-O-M-M-A.
Yeah.
Oh, yes, I have seen that one. No, we're not yet. No, I mean, the idea here, I kind of forget some of the context of that. I don't know if you
So
want to share.
they have an OBD2 plug, right? That plugs in your CAN bus OBD2 port. Lack of a better explanation, the fancy dash cam goes on your car, and it gives you full autonomy, like, I forget which way the levels go, but it gives you full driverless autonomy on your car.
That's right. Okay. Yeah, it's a kit that you can add in, like a thing that goes on.
It's an open source project, right? So there's forks of it. So I'm curious how much you guys build on.
Yeah, I mean, there's the challenge of working in a highly dynamic space where that definitely came in since we started this project. So it would be really interesting to leverage some of their tools. Like we're not too full of ourselves to just borrow somebody else's implementation if it's open source. We just integrate that in. So that would be a really good way for students to be able to appreciate and bring in some tools into our stack. That We don't have a vehicle where that would work particularly well, but that would be a really compelling use case if we could get access to a vehicle, like a standard vehicle like that. I'll show you the vehicle that we use.
You could.
We've now compromised it enough that it won't use that. But that's a great point.
The other question is, are you guys building an API platform for anything you guys build?
So I don't know. My understanding of API may not be the right, so it wouldn't be an API per se, but it is an open source library of these ROS2 nodes that then could all run. And so the idea would be that you could leverage, anybody could borrow those and run those. Because it isn't, it's not something like running on a server or anything. It's all running locally on our.
Right, but you can communicate to it and then let's say, interact with it, or you're doing a commercial thing, right? So it's delivery, so I can type in my PIN and open the door, right? Or it arrives to me.
I see. Yeah. Oh, I mean, that would be really cool. I mean, one of the stretch goals many years is a taxi service on campus. And so there we build in a lot of these hooks, I think we're just maybe not as far along as kind of what would require that. So that's a great point. Yeah. Anything else? Yeah, maybe this gets to your point here. So actually, both of you guys. So vehicle engineering is a really large part. So about half of our team right now is working on various pieces of our vehicle. So one of the biggest limitations there, now I showed you a vehicle, the Zoox vehicle is a specially designed vehicle that Amazon has made just for their autonomous driving. But a lot of other people are essentially using Camrys, Toyota Siennas, whatever. They're just like leveraging these and essentially reverse engineering. Many of them have some drive-by-wire capability, but it's not, a lot of them isn't quite sufficient yet. So there's a ton of reverse engineering that goes on in order to build out these fleets. And so that's one of the biggest things that's kind of slowed down, I think, some of the propagation of this is just that implementing this on some of the vehicles has taken a lot of time. I think they're slowly getting to the point where a lot of the vehicles have enough where these built-in solutions, essentially the drive-by-wire is capable enough to just be used. But nonetheless, undoing what was never really meant to be undone is challenging. And if you could zoom in on that picture, you'd see lots of nasty wires. And so once you open up some of those nicely, tightly bundled cables and try to figure out where a wire goes, it's a mess. So it's a challenge, both for the industry and for us. I talked about our vehicle. So that's our vehicle. We picked this vehicle for a couple of different reasons. I didn't want anything that, so I wanted something that the students could work on. I didn't feel like a modern car. I was confident in students opening that up and starting to change things in our ability to get it back. This is simple enough. It is not a golf cart. It's called a low-speed vehicle. Technically it's a Polaris Gem. So if you've ever been to like downtown New Orleans and need to like take a little shuttle, you'll see these, or sometimes these are used as like the groundskeeper's crew stuff. One of the nice things is that they have a CAN bus system that communicates between all of the components. So it's a little bit more legitimate. The battery is actually a lithium-ion automotive grade battery. It does things like regenerative braking. So there's a lot of compelling car-like characteristics without being as complicated as a genuine car. And so I had a undergrad senior design project actually retrofit this for drive-by-wire, which it was not originally meant for. And so they replaced the steering column and the power steering unit there. So that was things I was comfortable having students do without them essentially bricking the entire vehicle. We've outfitted it for drive-by-wire. And so now you can essentially drive it by a joystick. That's one of the ways you can test drive-by-wire. You can do gas, brake, and steering all different ways. One of the interesting tidbits there is the fact that all of those have to get accomplished in completely different ways. So it's not like computer control those three different things in the same way. Everything has to be done differently. But in addition to the drive-by-wire, we outfitted with a ton of sensing, and we've been really pleased that the school has really supported this. They helped us buy some of this equipment. So we've got a really high-end 128 scan LiDAR. Those are really, really high-end and kind of like better than anything you find on a deployed car right now, just simply because they're that new. So we have a lot of really fun things to play with, and that gives students an opportunity to kind of experience all that great hardware. One of the things that I have on my roadmap is building out what I call a third scale car. And I have to be careful talking about this because it is a kid's ride-on car. So it's literally what you might buy for not my daughter because it's $1,300, but it is maybe somebody's daughter. But so it's a kid's ride-on car. You could sit in it. Technically, I could fit in it. I'd be a little uncomfortable. And so it's that big. It has that kind of carrying capacity. And the really compelling thing about this is that I'll show you a little bit more about what I do with security and safety. I believe that if we really want to work at the juncture of safety and security, you actually have to be willing to make your car crash. Like that's not something I'm going to try to do, but if I genuinely are going to keep my car that far away from things that I'm never ever going to crash it, I can't really make a compelling case that I'm working in safety and security. So this vehicle, I don't want to hit anybody with it, but at least it certainly won't kill anybody. And again, that's not the goal, but that's just simply to talk about operating at this interface of safety. There's some amazing programs that are full scale. Honestly, I don't have the money to do full scale, so that already eliminates it. But it also means that if we deal with this smaller scale, we can actually do the safety thing. There's these tiny cars that are called 10th scale. So they're essentially an RC car that people load up with all the same kind of equipment, but it's not actually the same automotive grade equipment. So instead of like a 3D LiDAR, they've got a 2D LiDAR that's just scanning in one plane. And so there's a lot of caveats, and especially with the computation, you just can't support the right things on a small platform like that. And so this is the platform where you can do everything that you can do on a big car, full scale car. But it's small enough that it's replaceable. I can make a couple of these, and we can have really start getting at connected driving and safety and security. So that's kind of the pitch for that. That's something I'm building out. Again, retrofitting these things is tricky, and so we're kind of partway through the process of making this, and then hopefully making a couple of them so we can start doing some interesting coordinated things. All right. I'm going to go through this kind of at a high level, but I just want to give you an appreciation of the perspective I take on security and safety and things like that, and then I'll show you just a few more things about an example of some student work. So where I came to autonomous driving was from this idea of safety and security, and it really comes from what I'll kind of summarize together as trustworthy automation. So automation means all sorts of things. In this context, we'll think about it as autonomous driving. Could be a manufacturing system. I started out with process control systems. That's one of the things you'll see immediately after this. And the way that we kind of think about trustworthy, we need to make sure that it does what we want it to do under all sorts of different circumstances. And that could be faults, and that could be normal operation, because there's enough weird things that happen in normal operation. But we're really motivated by understanding what is the true envelope, what's possible, based on our understanding of this system. And so that is what leads me to the context of attacks. And so there, in our control system, that's my background, you have a model of your system, you have something that's controlling it, that's turning valves on and off, turning left and turning right based on decisions. And the question is, what happens if you can no longer fully trust the information that you're getting back in order to, as feedback, in order to make those decisions? And so the high level idea is the fact that if there's a lot of reasoning that we put in place that filters out the possibilities of truly large and anomalous attacks. And so one of the ways to think about this is if you're sitting in your car and you're simply doing cruise control, so we're just trying to keep the car going at the same speed. And if all of a sudden I'm reading my speedometer and I'm going 60 miles ahead forward, and then the next time step that I'm going to sample is 1 second later, now I'm going 50 miles an hour backwards. There's just no physical way that, first of all, my body made it through that transition, but there's no way that the car could stop and go back to it. So there's some limits physically that this system just can't go through. And so that's the kind of ideas that we use on physical modeling and physical limitations of these systems in order to essentially put bounds on what's possible and what's not possible under attack. And so that's not to say that you couldn't cause an attack, but that those kinds of attacks would be easily identifiable and detectable. And so we kind of, the kind of work process that I go through is identifying detectors that monitor this process and identify when something completely anomalous is happening that essentially is at odds with the physical behavior of the system. And so this is, again, kind of security or anomaly detection from a physics-based point of perspective. Those are the physical constraints that are imposed based on just kind of what I know the system is doing. And kind of at a high level, what we're doing is we are understanding what are the different kinds of uncertainties that are in place in the system and how that maps into what an attacker is able to do. What this attacker is able to do without me being able to detect it. So if I have a really lousy model or understanding of my system, and there's a lot of noise in my system and uncertainties, then I don't really have a good way of predicting what it should do. And so that makes it more, an attacker more capable to inject a large attack without me knowing about it or being able to detect it. Because there's a lot of noise and uncertainty and variability that's happening in the system every day. And now I have to determine what's going to happen. And I won't be able to do a very good job about that if I have a really poor model or very high uncertainty. So there's this coupling between, or this mapping between the uncertainty of a system and the amount that an attacker is able to exploit it in kind of a stealthy manner. So that's the spirit that we've analyzed a lot of these systems. And so just to kind of at a high level, what this does is there's a lot of math that goes into this, but we come up with an equation that looks something like this, where this parameter is essentially this level. And so what we can do is we can predict kind of how bad things can be under these attacks. And the important thing here is not really what's on the slide, but simply that all of these parameters represent some information about the system that I could have a chance of knowing. So I have a chance of knowing, like a spring constant of a contraction, or the speed that I might go on something. So that represents all the system information I might have. And then the attack, if I impose certain kinds of detection mechanisms, I can limit these attacks, essentially be better at limiting them in certain cases than others. And so the really important thing is that we have this predictive capability that takes uncertainty and system characteristics and map it into attacker impact. And so what that means is that so this is a model of like a tank process and a process control. So given this model, given my detectors and all this other stuff, I can now put a stamp of certification that says this system is not going to get any worse than this if I employ this detector. And if you tell me that this is okay and you can deal with that system, and it's not going to make something blow up, then we can give that a rubber stamp that says this is safe enough for, not blowing up. And so now we have this guarantee that we're able to accomplish because we can figure out what's the worst things that can happen. So it's really the spirit by which we go through this. And in the context of an AV, and I'm going to start migrating past some of this more academic stuff, but in the context of these AVs, one of the where this goes is that kind of level of how bad things can get. Essentially, one of the ways you can think about it is we're going to propagate the uncertainty of this autonomous vehicle, and it's going to create this envelope around the vehicle. And so what that says is maybe my GPS signal gets corrupted, or maybe my attacks get compromised, or sorry, my cameras get compromised. So what's the worst that could happen based on all this decision making my autonomous vehicle is going to do? What's the worst that could happen in order to understand what this car could end up doing? And so this creates this envelope, and as long as I drive this car such that this envelope doesn't hit this pedestrian, doesn't hit this car, stays on the road, then I can again have this rubber stamp that says this is somewhat safe. And that's because under all these different scenarios, I'm modeling all this uncertainty, this vehicle is going to be somewhere in here, but it's going to be within this envelope. So as long as I keep that envelope away from things, I won't crash. That's kind of the idea. Yeah, is that a question?
What's the probability that a camera would go out?
Well, I mean, we are designing, oftentimes this analysis.
Can a camera go out?
So it could, so somebody could inject some malware in your, or they could, there's some other known attacks where you can like,
Point a laser at it and pull it out.
Disappear or disappear on the camera.
yeah, you could have phantom objects on your camera, stickers that might confuse it.
What are the environmental factors that affect the camera?
What are the environmental? Well, I mean, like performance, like rain and stuff would certainly degrade performance depending on kind of your decision making. Yeah. Did you have a follow-up?
Yeah, I do have to more.
Yeah.
What's the protection from a breach?
Well, and so that's a really great question. So that's why the stuff that we do is often really not thinking, or I usually say it's orthogonal to a standard security approach, which is to say, let's keep people out of the system. Let's harden our system in order to make sure that they don't get in. My analysis says, okay, we can't guarantee that nobody is not hit. Sorry, there's too many negatives. We cannot guarantee that we don't have it. So what kind of detection can we use from the physical process? So in some ways, like, encryption uses a key. And so the key that we're really using is the physical behavior of the system. And so we're using that as a constraint to limit what we allow as acceptable. And so we are assuming that someone could totally get in and totally compromise those. At this moment, like, for example, a lot of this analysis does specifically look at what happens if something happens with our sensors. There's another question what happens when you have actuator faults as well. So there's a lot of different iterations, I suppose, you could do of this. But we don't assume no attacks. We assume that you could have attacks.
So your actuators have sensors tied to it.
Say that again?
Your actuators have sensors tied to it to pick up that information.
Yeah, through the so if we accelerate, that's actuation. We can measure that based on our speedometer to know did that translate into additional speed by accelerating? Yeah.
Is this where you deal with the moral dilemma?
Trolley problem.
Yeah.
The lady sets off the curb with the baby, you gotta kill either her or you crash your car.
Well, in order to guarantee, we would like to be able to do this for all scenarios. But yeah, I mean, I suppose there could be scenarios where there is no way to guarantee safety, and so that leads to a very challenging question of being able to say, let me somehow specify all of the things in this environment. Yeah. And how can I say, because if there's 2 cars in this environment, maybe I can guarantee safety. But if there's like 5,000 cars packed in here, obviously can't move, right? So then the question is, what does it mean to guarantee under different kinds of scenarios? Because every scenario is very different.
You gotta make a choice between 2 bad choices.
Could be. I mean, ideally, your planning horizon is far enough that you never get into that situation. That's how you would guarantee that you'd never reach that. But that's a challenging thing to do.
Yeah, I think gentleman was referring to the only moral problem. Killing 1% versus 2%.
Yeah.
I have a question about it. I used Waymo about 5 years ago before COVID in Phoenix. That's where it started, and now many cities use that too. I heard, but Tesla and others, they don't have the full self-driving car out there. I heard the main problem is not the technological or electronic thing, but it's more political and regulation and the lobbyists against and for it. That's where it got started.
You have to cars insurance. So insurance. Can't get cars insurance. It's the biggest challenge.
I mean, I think that so I said that the commercial is definitely leading this charge, which is true. If you look back at like Carnegie Mellon many years ago, back in the 90s, they had something that already had some self-driving, possibly better self-driving than what we've got in my vehicle right now, but we won't go into that. But so much of the problem is solved. So if you stay on the highways, if it's sunny, if people are behaving well, it's not a hard problem from an engineering perspective. You get enough smart people to write enough code, you can do this well. It's all in the edge cases. And so I think what you said has a lot of truth, is the fact that there's got to be adoption at some point in time. How do we determine what's safe? And is that benchmark based on human drivers? Is it benchmark based on an ideal? And so those are the challenges, I think, as a society, we have to collectively decide.
I was referring to political issue.
I think that's
somebody else's code, and they have the lobbies against this.
Oh, well, I would say that just kind of generically as a society, we have to convince each other of this. And so I think that that's probably the bigger challenge. I think I already know that not everybody in this room would get into one of those vehicles, which is fine. I think that that's a reasonable choice at this point. Some of us would. And so, would you let your kids? Would you let your 5-year-old? So like at what level are you confident about this?
Well, this gets into the question, I said insurance. There's a big outstanding question of liability.
So Texas, we have a pretty good code. It's essentially whoever owns the vehicle is liable at this
But
point.
then the manufacturer, it's related defect, etc.
Yeah, you probably have a case to sue if you get sued, you could sue them. So yeah, that'll be certainly.
Again, this regulatory thing does get very clouded quickly, right?
Justin Rashida has a question.
Yes, yeah.
So can you help me understand what that envelope consists of? Is that like the range of the sensors or?
That is, so
Justin, can you repeat that question?
yeah, so she was interested in understanding kind of what goes into quantifying this envelope. Is that right? Yeah, so what I was trying to say earlier, which I may or may not have done a good job, is that there's certain types of uncertainty that get injected into the system. Could be like how good our model is, what kind of uncertainties we're dealing with, like with our GPS, it could be plus or minus a meter or something like that. How does that all get propagated through into my certainty of, in this example, where this vehicle is, my location of my vehicle? And so I'm in this one, I'm just kind of schematically showing that I'm going to have some uncertainty in my GPS, and I'm going to have a crude way of localizing myself that's just kind of based on that and the dynamics. And then I'm going to propagate that uncertainty in order to say that this vehicle is here, but because of this uncertainty, I don't know for sure that it's exactly there. That's where I'm going to place my estimate. I could be anywhere actually in this whole envelope based on my normal uncertainty. So what this envelope represents is this uncertainty from the GPS propagated through the dynamics and into kind of my state space, my XY position, say, of that vehicle, which is the same kind of idea as here. I didn't show you kind of where the uncertainty came from, but this is kind of like one of the states of our system, kind of how far it got. And so this envelope represents kind of how far that those XY positions can go. And then here, what this is kind of trying to schematically show is that this red vehicle represents essentially what an attacker can convince you that your vehicle is here, even though it may be here. And so that red vehicle has to stay within this envelope. Otherwise, our detectors that we've designed based on these physical constraints would be able to tell you that you're being attacked. So all right, you got a question?
Yeah, first of all, thank you for the depiction. It really illustrates a lot of first. But in San Francisco right now, Waymo is pretty successful. You can actually rent the Waymo as a rental car from SFO Airport into downtown, and it's amazing how well it is doing well. So, is what you're doing going to be equal to that or beyond that? Or what's the end game here that you're looking to accomplish that you'll get to from an alternate ticket Waymo being where it is?
Yeah, no, it's a great question. So it kind of goes back to they're doing so much, and I'm not going to compete with them on self-driving specifically. So yeah, so the kinds of things that I would like to help them with or help the community think about is this idea of, they've got self-driving pretty well nailed. I mean, as well, they're doing about as good as anybody else could be doing right now. But none of their self-driving techniques are specifically hardened against attacks. So, so far we've had, unfortunate incidents that have been because of environmental factors that essentially lead these vehicles to do something odd. We have yet to see a autonomous driving vehicle get hacked and then cause a problem. And that's a potential future that I think exists in the future, probably not so far in the future. And those are the kind of things I would like to contribute to be able to offer techniques to essentially analyze what they have, the code base that they have eventually, but also to maybe help redesign some of those things or some of those algorithms in order to have these detectors in place so that we could shut the car down faster if we detect these attacks. So that's kind of the idea. Yeah.
So with that, related, so the way I see it is you've got your environmental factors. It could very well be for the anomalies, right? Mm-hmm. So you could have a sensor failure It's probably very clear and there's probably redundancies, but just let's go with anomalies. You have a sensor anomaly, sensor drift. That's one case. You've got environmental variables. Maybe the sensor is detecting something odd, but because it's coming from the environment, whatever that thing is. And then you have the attack. So trying to figure out, is it an environmental anomaly, is it a sensor anomaly, or is it a legitimate injection from a safety perspective, or does it even matter and just treat them all?
Yeah, no, it's a great point. And so a number of the things that we did in the context of this kind of process control work was really focused on this idea of the tolerance of, there's this kind of triangle of well, maybe balancing act, say, between sensitivity, like how sensitive we're going to be to these attacks, how quickly we're going to be able to detect them, how small we can detect them, and the amount of false alarms we get. And so this is kind of what you're getting at, right? And so as an operator of a very large chemical processing plant, you're not going to want to have to deal with false alarms that happen all the time. In fact, there's definitely literature that exposes the fact that there's fatigue to false alarms. So that what would be alarms are no longer alarms because people just get used to the seeing them. And so so that's a really hard question. And especially in the context of these safety critical applications like autonomous driving, where, yeah, maybe like a concrete scenario could be, you've got this either camera or a LiDAR, something that's giving you information. You get some dirt on this. It's now identified as an anomaly that, you know, you're seeing reflections like right at your vehicle. So you have some logic that says, okay, well, we're going to make this robust to a couple mud splats. So let's write in some code that essentially now eliminates that from our sensing. And now there is critical information that you could have detected because of that would have avoided you to hit somebody or something like that. So that could be a sequence where you're trying to do the right thing, you're trying to fix some problems, keep it up and running, and then you run into a problem. So yeah, this idea of how sensitive to be is a really important topic. Yeah, that gets into, like, as a driver, you know, how do we make people accountable for if they get a flash that says, you know, you need to pull off and clean off your sensor, if they actually do that? Yeah, that's a really great question. I'm gonna skip over some things that we've been doing more recently to kind of like generalize that anomaly detection stuff. But I just kind of want to show you a couple more tools. I think we still have a little bit more time, where these are just some of the things that we get to play around with, students get access to and get exposed to. So a lot of what we do gets tested in a photorealistic simulator first. So this one is called Carla. And so it's essentially like Grand Theft Auto, but there's nothing weird happening except for our driving. And so what we do is we can control this vehicle, and based on, it has the same raw stack that we build for our physical vehicle. We use the exact same thing with a few tweaks based on kind of car parameters and everything. But that exact same logic stack essentially runs in this virtual environment that we'll deploy on our car. And so there's always a little bit of a gap between the simulation and reality, but it ends up being a really nice, compelling way to test out algorithms. Let's see. This is one thing that I would like to kind of talk through, just because I think it's a really compelling example of how we can use some of these rigorous tools to get us to a point of better algorithms. So SLAM is simultaneous localization and mapping. So it's the way that many robotic systems essentially look at the environment, map that, and then also figure out where they are in real time. So there's a lot of applications where GPS is not perfect. So GPS has already got plus or minus quite a bit of uncertainty if you want to talk about staying in the middle of a lane. In addition to that, there's a lot of indoor robotics applications where that isn't available. And then, and so what you're going to do is you're going to use a lot of other sensing in order to figure out what it is. And the way that I think about it is it's a little bit like Spider-Man. I identify a feature in the environment. I'm moving relative to that feature. That allows me to kind of know how I moved relative to that feature. And if I'm tracking enough features, I've got enough things kind of triangulating and keeping all that information in place, that I can kind of track my motion relative to all of these different features. So there's a big challenge of identifying these features. And so that's a vision processing task. So I'm not going to talk about that, but that is a really important task. One of the things that we've been doing with our tools is trying to build, again, this kind of notion of trustworthiness. So the way that most SLAM methods work, I talked about this kind of Spider-Man slinging, kind of keeping things triangulated. So what they'll do is there's always a little bit of uncertainty when you measure something. So you can't just assume that I know exactly where that feature is relative to myself, because there's always a little plus or minus, and then you move and you'll get another plus or minus. So there's a little bit of fudging that you need to do in order to make that work, that triangulation work. So the way that they do it is they take a Gaussian distribution and they plop it on your measurement, and they just assume that your measurement uncertainty is this Gaussian distribution. And that allows this fudging factor to make things line up, and allows you to optimize to get what's considered the best result. Turns out, and this is one of the things that we've proven, it's a little small on the slide, but these little blue dots represent essentially this estimation of this conventional slam. One of the things that we can show with some of our guaranteed tools is you can track all of the different possible places that this vehicle could move as you move along. And sometimes, and most of the time, this little blue original slam is going to do a really good job. It's going to give you something that's pretty close. But it's going to give you something close, but what we're showing in our sets are these little green shapes. And so what we show is that this really good guess, that's the blue dot, that's our conventional slam, is actually giving you something that's close, that's actually completely infeasible based on all of these constraints that you've got. So if you had a real uncertainty that you could quantify, and then you propagated that through using some of our tools, then what you can show is that that original slam gives you something that's close, but that's not actually contained in this feasible set. And so if you want to, again, provide this rubber stamp that says that vehicle is going to stay away from this cliff or stay away from this pedestrian or something like that, right now this is a small error, but there's no saying that this couldn't grow into something larger based on certain scenarios. And so then this idea of this rubber stamp just can't happen in the context of these conventional algorithms. And so there's a whole host of these that are used currently in autonomy stacks that are really clever, really amazing heuristic algorithms that give you good results most of the time, but then there are just some scenarios where they just don't quite work. And so that's another area where I would like to contribute, is to offer alternative methods that allow us to give us this rubber stamp. And maybe it's a little less performant in some of the ways that we would analyze it. It's a little slower in some cases, but the idea would be that we can actually provide some guarantees. And so that's one of the things that this example kind of demonstrates. Yeah.
In the SLAM scenario, what's the latency between speed and the triangulation correlation with the triangulation into the decision process that comes up to do it?
Yeah, no, I mean, that's a really great question. Yeah, so that is something that we have not incorporated into this particular simulation, but that would be totally based on whatever embedded systems running all of this. We try to get it down to 10 hertz usually on our systems right now, but because there's not only the latency, but then there's the computation that happens based on inferring based on all this triangulation, and then trying to update because maybe by the time you solve that, you've already taken new measurements. So yeah, that's a real challenge. Yeah, this is one of those things where each iteration you kind of add one more effect on top of it. For sure. All right.
I was going to ask, how many, because there's lots and lots of sensors and new sensors coming all the time. As you start getting more divergent data with varying levels of precision, how are you factoring that into the SLAM?
That's a really great question. So I think one of the neat things, I'm kind of jumping between a couple different lines of our work, but one of the things that we can do with some of these kind of similar set-based tools in the context of our anomaly detection work is to demonstrate that you can add new sensors that actually make your ability to detect attacks worse. So you can add new sensors, and they may just be adding nothing, or they could be actually making things worse because they're essentially exposing uncertainty that somebody could exploit.
That's what I was kind of getting.
Yeah.
So you're now going, as the number of divergent sensors increases, you're seeing a decrease in.
Yeah, so you definitely want to make sure that's what a systematic analysis could potentially reveal is how to select the sensors, how to complement sensors that are currently inadequate, how to add new sensing modes, and kind of what uncertainty could be tolerated in order to grow that in that sensing suite in the best possible way.
Are you looking at other algorithms besides the standard anomaly equations as well?
Can you repeat that for the, so,
So we're largely talking anomaly detection for
Yeah.
the most part. Are you looking at other AIML equations as well besides the
that's a good
traditional
question.
suite of anomaly? Right.
so there are a lot of different ways to detect anomalies and a lot of different definitions of what an anomaly could be.
Well, there's other things besides anomaly, right?
Yeah,
Right.
and so, yeah, we would like to make our tools as general as possible. One of the, I didn't go into a lot of detail, but one of the main things that we have is what I generously called a model. And so this model could be a lot of different things. That's essentially what predicts what we expect to happen. And this is essentially what it's a model-based anomaly detection, which is not the only kind. But your model could be a data-driven model. So it could be a neural network that's going to predict some traffic or something like network traffic if you wanted to apply it in that context. So we attempt to be general in our ways, but there's always some other mechanisms. I think this idea of propagating uncertainty into attacker impact is something I would like to try and have other people that are developing similar methods try on their own. Yeah.
You may have already answered this question earlier, but what's the environment you're looking to really launch this into? Obviously, probably not going to be something you're going to be like throw it out there. You know, what's the ideal scenario you guys are picturing of how to get this introduced? Is it more like an HOA scenario or a college campus?
Oh yeah, that's a great question. I think if you could drive on our college campus, you could probably drive anywhere. So that might be the last place we end up deploying. No, but it's a really good. It would be a great test. I think we would probably start mainly. We would always have a safety driver, and we do drive. So one of the reasons why I got that vehicle is because it is street legal. So we do drive on city streets. We just have somebody ready to take over at any moment. So we can do that. Those are like neighborhood streets. Those are actually pretty easy. I think we would probably start, especially with those third scale vehicles, in some kind of like artificial constructed scenarios, like in a parking lot, honestly, and then kind of grow from there. I think with the Carla simulator, we can try things out before we kind of bet that we're close to being reasonable. It's a long horizon though. So, I mean, eventually I'd love to have a shuttle that goes between UTD and somewhere else nearby. We have a place in a Richardson IQ that we'd like to visit, so that would be cool. That's a number of years down the road.
Yeah. Are you aware that the company in Dallas, Mosey, that's building self-driving buses?
Mosey? Oh, yes. Yes. There's so many of these that it's really hard for me to keep track of and keep tabs on all of them, but I have heard of them. Yes. And I think I've had some email introductions to them. I mean, there's a hard problem and one that clearly is not completely solved, and the community is completely not bought in. So I think plenty of work still to be done on this. I think one of the challenges, again, this is a commercial problem. Deploying that is a hard problem still, even though it's an engineering effort. And so I don't think that we have a whole lot of added value thinking like 10 years down the road for them. So that's where the cities, the governments, these are the people that are going to care about what we're doing, thinking that far ahead. But I could be wrong. I could be great. Yeah.
So I remember that about 35,000 people die in car accident in the US every year. But I got the exact number, like so many people for a million miles driving. So do they have a data for Waymo so that we can have some reference point better? There will be less death if they have auto.
I think that's the compelling argument that they are definitely trying to make. Yeah. I don't have those numbers for you, but yeah, I'm sure that they would tell you how many incidents they have per million miles driven.
So does Waymo have those kind of data? Or?
I would expect they do. I don't know offhand. I can try to find it.
That's the end story. Like we want the number of.
Yeah. I think societal acceptance is really tricky because again, I don't know, or collectively we don't know what benchmark we're using in order to decide whether that's an okay number. And that's the challenge. But, one of the things I reflect on is, it's my personal perspective as we go through this AI boom, is potentially this is a way that many people might either decide one way or the other, whether they're going to get into a car, is based on, just using ChatGPT on a daily basis. Like, that might be enough to make somebody feel like, okay, I'm willing to accept this. That's the same as getting on a random, airline and not knowing who the pilot is and being okay with it, right?
Well, okay, so are you sure that's the same?
I'm not saying that it's the same, because it's certainly not. You're not getting in a safety critical when you ask it like for a home form. But I'm just saying that it's a familiarity now with these two tools that people wouldn't have had a number of years ago. But this is definitely a more philosophical end of this debate.
Yeah.
Yeah.
I see an article here that does say that the number of accidents decreased with Waymo,
Mhm.
but we have to check the authenticity though.
Mhm.
But on a quick search,
Oh,
there's
okay.
an article like that.
Okay, the way most people argue that the more autonomous vehicles out there, the fewer human drivers, the fewer the mistakes are gonna be.
Human trust is not statistical.
Yeah.
It's experiential.
Yeah, maybe that's an elegant way of saying what I meant to say.
I think mixed driving, whether it's autonomous and human-driven vehicles, is a more difficult problem to solve than when they're all autonomous vehicles and they're communicating between each other, among each other. It's much
It's almost
easier.
impossible to predict human behaviors, especially when somebody like has a seizure or something, or, all
That's the
wheel,
In every large system, the key issue you always struggle with in a single word is integration. And whether it's hybrid, decision-making model, being digital versus human. I do have some other questions since I don't have the mic for the second here. It seems as though we do have technology in inertial IMUs, cold atom technology that's highly precise, interferometers that are reliable. Certainly DARPA spends a lot of money seeing to that for various reasons. When I look at this problem and I think about it in the same way you might, when you think about the idea of getting consensus and having geospatial and vectorial velocity confidence, and of course boundaries being a big part of the event that goes. What is it when you in the hardware world you think, if at all, will make the difference? And we'll get into the security aspect of hardening it, but just getting to the actual mechanisms that give us the confidence, no matter the environmental factors or other factors that might play in aside from security.
Yeah, I guess. So my read of the question is that there's a lot of really good technology to be put into, especially the localization and understanding of the vehicle ground dynamics and stuff like that. So one of the things that's challenging is that we would have a hard time knowing the ground truth of everything around us. And I think that's where the problem becomes tricky, because then it's the prediction of, and we're using images and other things in order to figure out where they are relative to us. So certainly our location is a really big, important piece. And that's kind of what I was just, that's kind of what I was focusing on here. Right. But there's the whole other piece, which is, how do we perceive how far we are from this and from this and this? And how do we even know that we didn't miss something here? And so those are other edge cases that would be challenging to improve using the same hardware.
Yeah. I have a client that's in collision center business, and I'm up at the larger levels and what's happening in that environment. He's very interested, obviously, in this conversation. And I decomposed that model and got it down to those things which are causal, which are reliable predictors of demand for collision services. Okay, so we have severity levels within collision, typically based on energy states at the moment. A collision, you're moving faster, you get more severe damage, right? 44% of his business is what we call level 1, small things, right? Mostly bumper on either side, related to congestion and distracted driving. Mm-hmm. Okay, as long as you have congestion in a growing market, you have people who are distracted. you're going to have lots of severity 1 business that's very stable in demand, right? Level 2 is a little bit more energy, higher velocities, et cetera. I guess my point being, when I look at his workloads and I look at the severities, it is more rare because of ADOS and other instruments that help people, let's say, intercept bad behavior, right? That we are seeing some factors, because I did a peak evaluation on his business showing that by the time 2028, it'll be decreasing because of the impacts of technology and all these other factors, right? So when you think about now this technology and moving it to this idea of lowering the incidence of human casualty, things that are broken because machines ran into them, do you think that's a fair reference in looking at statistically, how much can I take down the severity 1 incidents? People who are busy in congested traffic, just bumping into each other. I'd say we could go a long way there with autonomous. And that's how I'm processing this a bit in comparison to my other types of experience around automobiles in the industry. Do you think that's really the way the industry will process this and then look at, okay, we can stop 80% of level 1 collisions. We can actually impact 70% of level 2. ADOS is actually helping with level 3 big severe things. I mean, how do you think about this problem? Because I'm just an analyst.
No, I mean, the points you're raising, I think these are the ways that we will have to find it if we want to reach acceptance of the technologies. That will be some of the arguments that have to get us there, is just kind of like statistical improvements in all of these different essentially incidents that happen on the road. I think that again, I think that kind of what you said, the experience, people will have to have experience. I think, as the technology, car technology definitely creeps its way along. So it's like many people have ADAS in their system, the automatic braking. Some people hate that. Some people, enjoy it. Some people need it. As that becomes standard, maybe the next phase will become more standard. The next phase will be more standard. So,
so evolutionary.
It could, that seems like the most natural thing, unless that there's a step change from somewhere, but I don't know. Maybe let me just offer maybe one. I think I'll skip some of those more specific things that we've done in our group, and I'll just kind of jump to this last slide or two, where I just kind of sum up. I'm trying to identify kind of the opportunities. You guys are all really engaged and technical people that are now in the community. Many of you have worked or are working, and so kind of a number of you I know are already plugged into our capstone program, so you're already kind of integrated in this. Just to form an idea, kind of like what we can offer, what kind of like how we can interact, academia and industry. I try to build students, find students and curate them, and then give them opportunities to demonstrate what they can do. So there's clearly an opportunity for businesses to recruit from my group, from this undergraduate group. So that's one of the things that I try to make sure that they have really great opportunities. We have some spectacular students and some people going and doing some really cool internships all over the place. We also do outreach, and so we do community events, we do schools, but we've also come to businesses and to just talk with your technical folks. So we've gone and it was like a credit card processing group that we went and talked to that just were a bunch of fun engineers and they wanted something to talk about. So we went over and chatted with them. So there's certainly an opportunity to enrich a workplace event if that's something that would be interesting, gives us context and helps us understand the students and I. And then of course there's places where, if we find the right topic, there could be something to do with research. Those are the kind of ways that I saw as opportunities to engage. And maybe the last thing, I'm going to leave you with this set of videos. If you just Google YouTube Zooks, you want to learn about and just see some really cool videos about self-driving, just go and you can, there's a couple of series called these names: calibration, localization, mapping, perception, computer vision, simulation. They're really fantastic. They do a really nice job making them, and they're just really fun to watch. So if you want to dive into this a little bit more on your own, definitely go and check out those videos. Many of my outreach things, I simply just play this video and add color commentary on top because giving people
Did you do a search for YouTube?
YouTube and Zeus. I really think they've done a spectacular job with their videos. They have a lot of them, but there's a series like this that have these topics in there, and those are really spectacular. So the last thing I just want to talk to you about is, so I'm involved in mechanical engineering and in systems engineering. Those are my appointments, but I work with students all over. So in mechanical engineering, we're starting thinking about essentially offering this notion of what I call like a focus track or a specialization. They have a number of electives. They could take a sequence of those technical electives in order to gain some sort of specialization. That could be in manufacturing, could be in transportation. We could offer a couple of them. Similarly, I'm in the systems engineering program, and to date, that has been a master's only program. But starting in the fall, we're going to be offering a bachelor's program. And so similarly there, we already have plans to offer certain types of specializations, give students the opportunity to kind of pick these kind of subspecialties. So, you know, whether you offer your thoughts now or kind of afterwards, I'd love to hear thoughts. I've heard it both ways. I've heard some people that just say, you know, you could get an economics degree as long as you can solve problems, you can come and work for me. At the same time, I also hear people that say, well, you know, I'd really like you to be able to model in SolidWorks, and that's the main thing that I'm gonna search for. Or I really need you to do whatever VSLI design or whatever, pick some very specific thing or a specific tool. So I've heard it both ways. I'd love to get input on kind of how you see this notion of a specialization, what it means to you as somebody that's working in you know, in the field and industry. But again, happy to chat more about autonomous driving. There's a lot of really great comments, and really appreciate the opportunity, giving me the opportunity to chat with you and hear your insights on this and kind of what you all are doing. Thank you very much.
All right, great.